Hi, this is Team Localhawk. I'm Grant Lemcool with Max Friesen, Jamin Shaw, Anthony Waje, and William Tehan.
The motivation for our project started off by looking at legacy aircraft and current surveillance and/or reconnaissance aircraft in the field. We noticed that they're either large aircraft that operate from dedicated airfields like the Global Hawk, or smaller surveillance drones used for tactical short duration flights like quadcopters. Large drones are easily spotted, and smaller drones aren't the best option for long range missions. Both these aircraft are ill suited for operations in contested airspace. Team Local Hawk seeks to fill the gap by providing a fixed wing aircraft that will survey a target 1 mile away for at least 1 hour.
We condensed our objectives into the mission statement at the beginning of the project, that the aircraft will be able to provide continuous surveillance of an area within 1 mile of the ground station at a low altitude for at least 1 hour on a standard day while maintaining a low visual and acoustic profile.
With that in mind, let's look at that mission profile. The aircraft will take off from a 100-foot improvised runway, climb to 400 feet AGL in St. Louis. The aircraft will then cruise to the target 1 mile away at that 400 feet. The drone will then be able to loiter above the target area for 1 hour while relaying information back to the ground station. After that 1 hour of loiter, the aircraft will demonstrate evasion abilities and then land within 100 feet of touchdown.
Okay, with that in mind, let's take a look at our explicit requirements. Aircraft will be able to perform a surveillance mission. It'll be able to perform it while maintaining a low acoustic and visual profile. It'll be able to operate on this 100-foot runway. It'll operate from the manned ground station near the landing strip. 2 adults will be able to transport it, and it'll be operated in St. Louis, Missouri. So here are derived requirements. They all come from the explicit requirements. I'm not going to go over every single one because of time constraints. Here's our functional architecture. You can see the ground station on the left and the aircraft on the right. In the aircraft, you have a power management system that has a low voltage and high voltage pickoff. The low voltage pickoff goes to the receiver and all of the FPV and payloads. The high voltage goes to the ESC and then eventually to the motor. Here's our preliminary design concept that we ended up with at the end of December. You can see the inverted V-tail, the high wing, the tapered wing, the twin boom design, and pusher prop. Here's our functional requirements. Again, they all stem from the functional architecture and the explicit requirements. I'm not going to go over every single one because of time constraints. Here's our drag analysis. We did a very rough drag analysis based on a rough area calculation for our fuselage and a rough wing area calculation. Here's our constraint analysis. The eventual design point was an 0.5 thrust to weight ratio and a 1.5 wing loading. Okay, so for our trade study analysis, we used this nonlinear scale from -25 to 25. It allowed penalization and avoided ties. So for our scoring rubric, you can see our final scores on the right. We ended up going with a brushless motor and a propeller, a tapered wing, an empennage of a V-tail, a GO E-184 airfoil, and a retractable landing gear with a grass landing. Our fuselage structure was eventually decided on as carbon fiber. Here's our bill of materials. I'm not going to go over all of this, but the table at the bottom shows that our eventual endurance would be around 2 hours or something like that. Here's our bill of materials cost analysis. This cost wasn't entirely absorbed by us, as there were materials already available to us, such as the carbon fiber and foam. But other than that, this is the eventual cost that might be passed on to a eventual customer.
For tail sizing, we derived our tail area from our wing area, our tail's distance from the wing, and our desired static. From this, we calculated a tail area of 91 square inches, a chord of 7 inches, a span of 13 inches, and a vertical span of 10 inches.
Okay, so here's our Gantt chart from December. As you can see, the test flight was originally planned for May 2nd. However, we did actually perform this on about May 18th, somewhere around there. So we were ahead of schedule there. However, we never integrated our FPV or automation electronics, and this was because of ordering times and build times and various different reasons, which I'll go over in the lessons learned. Here's our final external design. You can see where the foam splits, or the carbon fiber fuselage splits off into foam wings. You can see the twin boom design and the inverted V-tail. The pusher prop would attach back at this plate. Here's our final internal design. You can see the battery compartment out here in this open area. You can see also the blue electronics areas and the motor area in red.
All right. And here was the first stage of our build process. So what we did here was we bought MDF board and we pasted together, and then we did a lot of sanding on that. Grant Limkel actually catted our fuselage, which had this unique shape, and then we did a lot of sanding on the MDF to prepare it for feather fill, which is the top right picture. After getting the feather fill applied, we applied 2 to 3 coats of that. After getting that applied, we sanded that, started around a 200 grit, and then went up to a 1500 grit wet sand. And then on the bottom left, you can see the fuselage put together after being molded. We did one carbon fiber layup, which had a few rough spots. Unfortunately, on one of the ones, we pulled it apart too far, which created a couple different holes in there. And then on the bottom right, you can see the plane put together in its entirety.
Okay, so this is the second part of our build. So we had 2 different methods of laying up the wings. The first was a failure. You can see it on the left here. We put wood spars inside the wing and laid it up. However, the resin seeped into cracks between the pieces of foam and actually cemented the plywood, or cemented the wood spars into the wing, so it wasn't actually able to be removed. So we had to throw that wing away, unfortunately. The second wing, we were able to build a wing jig using steel as the replacements for the spars, and these we coated with mold release and wax, and those were able to be pulled from the molds very easily. So that was our eventual way of laying up the wings. We did have some difficulties cutting the foam, which did set us back a little bit of time, but that wasn't as big a deal as the first wing layup failing.
Okay, and then here's our third part of our build. You can see this is where we kind of integrated our wiring techniques and put everything together that would fly the plane. You can see the motor in the very back and the battery in the front. We created steerable landing gear by attaching a servo to the very front bulkhead. And then we had a little wire going from that servo to the landing gear, and you can kind of see it on the left picture that helped steer the plane. And one of our issues here is we just needed some more weight in the front, which we did with some weights, which put a little too much weight on our front end. So we tried to move our battery forward if possible.
So with their preliminary tests, we saw that first of all, there were issues with the receiver and mixing channels, which affected our flight. But luckily, we were able to get that fixed and get the plane up and running. We realized that the rear wheels were way too far back. Also, the weight in the nose ended up putting too much pressure on the nose gear, making it difficult to steer. So that made the drone veer off the runway. So basically, these two things affected our CG, affecting our stability. We were also able to gain a lot of pilot feedback, which helped us improve our build before our second attempt. On the second attempt, the main gears were mounted incorrectly under the struts, so again, the plane was unstable. But there were also other nose gear issues, which ended up exacerbating the problem.
For our final flight tests, we repaired the damage from the taxi tests. We moved our rear landing gear forward, and that enabled our plane to more easily pitch up while on the runway. We successfully got in the air. We had a flight that lasted approximately 4 minutes. We ended up crashing when difficulties with aerodynamic stability meant that we were pitching up while approaching the runway. To solve our pitch up problem, we planned to adjust our static margin bar by moving our tail back. However, once we got back into the lab and did further calculations, we found that extending the tail back was not a mass profitable solution, as the added length of the tail spars moved the CG back with the tail. And such, we came up with an alternate plan to add a spar to the front of the aircraft with a weight on it, removing the 2.5 pounds from the nose and replacing them with a 0.8 pound weight on a spar to adjust the CG forward.
And here you can see that pitch
Seen
instability
in
on
the video, we can see the pitch instability leading to the crash. The crash also damaged our landing gear, necessitating that to be replaced. We performed sound tests to evaluate how well our aircraft fit our stealth design goals. We found that from 500 feet away, the ambient min and maximum encapsulated the minimum and maximum noise produced by the plane. The volume was measured with a Kasun test KT202 decibel meter, and we measured the ambient minimum, maximum, and minimum and maximums with the plane engine on in increments of 100 feet from the aircraft. As you can see, the data only shows a significant increase when we're right at the plane. This is due to the sound dissipating over a volume while we're moving away from the plane linearly. So any linear movement away from the plane has to the third power reduction in volume.
Evaluating our success criteria, we found that we met our medium success criteria. We completed all of our criteria that we listed to count for our medium success, and during our flight testing, we were able to fully fly our aircraft manually. While we do not have a payload to fully say that we met our medium success criteria, we theoretically believe that our aircraft can fly the entire mission profile. Some automation was implemented, but as mentioned before, due to how long we spent waiting for our materials, we were not able to fully implement our full automation.
With that being said, the future steps of this project would be to continue testing our aircraft for the validity of the aircraft itself. The next thing would be to integrate and test the FPV as the payload, and also increase pilot assist functions, and then showcase our endurance demonstration.
Okay, on to lessons learned. So the first part, our fuselage design, seen here, you can see that from the front of the wing, the fuselage does not project very far forward. This made it difficult to get our CG far enough forward. We actually underestimated the weight of the tail, and we ended up having a static margin of only about 7, so that's why we came up with our plan to put a boom on the front of the plane. And that's what we suspect caused a lot of the instability, along with the high lift airfoil, which I'll talk about in a minute. So future steps, we should design the fuselage to protrude a lot farther forward from the front of the wing in order so that we can get the battery further forward in the fuselage to act as a lever to drag the CG forward farther from the AC to get a more desirable static margin. So the second one is wing stiffness. We had a 6-foot wingspan, and as you can see, the wings are foam and plywood with 2 carbon fiber spars through them as seen in the internal design. So these 2 carbon fiber spars unfortunately did not provide enough stiffness, and we had a lot of wing flex in the flight test. So steps to improve this, we actually, after the flight test, we came back and laid up a carbon fiber strip underneath the entire fuselage and onto the wings, and that we did a wing flex test afterwards and concluded that that was sufficient to reduce our wing flex to a manageable amount. So that could have been designed in from the start, definitely. So also time management. A lot of the reasons we never got to integrating the automation was we were waiting on a lot of parts to be ordered. We were waiting on the team's collective skill level in automation to come up to a point where we could integrate these parts. Also, we didn't really get started on build until after Christmas, where we could have been practicing our carbon fiber layups and making the molds before Christmas. So, moving on, communication and teamwork. We did have a group chat, but it wasn't utilized as often as it should have been, and I will take fault for that as I'm the team leader. I should have been communicating better. Most of the next meetings were planned at the previous meetings, so people who weren't there never knew when the next meeting was. Moving on, knowing materials and tooling constraints during the design phase. So originally, the entire fuselage and wing, this entire forward part of the plane was planned to be one part manufactured entirely out of carbon fiber. However, the CNC machine at SLU does not have that 6-foot span and travel to do this part. So we had to break it up into these foam wings and the carbon fiber center fuselage. So we definitely could have known that from the start. We should have just asked the person who ran the CNC what the travel was. That's a lesson for the future. The last mistake that we made was using a high lift airfoil. So it made our tail calculations a lot more complicated. You can see here that we use this complicated calculation. We actually took the camber of the wing into account when we designed the wing. However, this ended up not being enough, as we got a lot of pitch instability anyway. So instead, we would like to use a symmetrical airfoil. Now, it doesn't sound good because a lot of large-scale aircraft do not use symmetrical airfoils. They need more lift. But at the scale that we're working at, the aircraft usually use high-lift airfoils just as a convention. Or they usually use symmetrical airfoils, I'm sorry. The high-lift airfoils give an undesirable moment characteristic that we saw in our pitching instability.
Okay, thank you, Grant. And for our final slide, these were our resources used to design our tail. And our tail was first designed using these and to size it. And then we went with a 10% upsize to give us a little more stability.
Okay, thank you. We'll be taking questions when we meet with everybody at the end.
Thank you. Any questions?